Hello guys, now we will discuss another very important law, which is Kirchhoff current law. So the analysis corresponding to the Kirchhoff current law is called as nodal analysis, because we will see further that we will be calculating the current through the nodes. So first we have to define a junction. A junction is any point in a circuit where two or more circuit paths come together. We may also call it as a node. So in this circuit, on the left hand side we have 9 volt and 3 resistances. We have basically two nodes here or two junctions here, and all three resistances are connected in parallel. Similarly, on the right side we see that there is we can clearly see that there are two junctions. So we see that if these are basically the wires configuration, actually there are actually only two junctions in that particular circuit. So Kirchhoff current law generally states that the algebraic sum of all currents entering and leaving any point in a circuit must equal to 0. So please again note that the sum is algebraic sum. If the current entering, if we take the current entering a junction as positive, then the current leaving the junction would be taken as negative. Similarly, if the current entering a junction are taken as negative, then the current entering the junction would be taken as positive. So please in this example see that we have four currents, I1, I2, I3 and I4. So here we have the current entering are I2 and I3, whereas I1 and I4 are the currents leaving the junction. So please note this particular equation, summation of In equal to 0, which is I1 plus I2 plus I3 plus I4. So in this equation I1 and I4 would be having actually opposite polarity of I2 and I3. The sum of the currents into a junction is equal to sum of the currents out of that junction. It is in easy form we may say that the current entering the node is equal to the current leaving the node. This is the simple form. In algebraic form we have to define the polarity of the current. So please note that in this example it is more clear that the current I1, I2 and I3 is taken as positive, plus sign because this is the sum, algebraic sum, and the currents I5 and I4 are leaving, so the current entering the node would be minus I4 and minus I5. So this would be the equation of KCL. Nodal analysis using KCL to solve for the voltages at each common node of the network, and hence determine the currents to the and voltages across each element of the network. So through nodal analysis we will first of all define the voltages across each node. If we know the voltages on every node, we will be able to find current in every branch of the circuit. So consider this same example. Here we have 10 volts and on the left side and 20 volts on the other side, and 3 resistances. So technically here we have 1, 2, 3 and 4. So technically we have 4 junctions and we should know their voltages. We know that the voltage of this junction here on the left hand side is 10 volt, and on the right on the left hand side bottom one has 0 volt, because this is connected to the negative of the supply. So we may call it as our datum node, the node which is at 0 potential. So and we know the voltage across the rightmost node, which is 20 volt. So we only need to know the voltage on the node at the center one. So how we will find the voltage at this node? We will find it through applying Kirchhoff current law. So we define the voltage, for example we say the voltage is VA. Now we have to define the currents. We will be having the currents I1, I2 which are entering, and I3 is leaving. So we have to define one form, current entering or leaving. So if we suppose this is this is how we are calculating. So how we will calculate I1 will be equal to 10 minus VA over 10 ohm, the V1 minus V2 over R. V1 would be the voltage of the point where the current is entering, and V2 will be the voltage of the point of the resistance where the current is leaving, and divided by the resistance. Just like Ohm's law, V is equal to IR, where V is the differential voltage across the resistance, I is the current through the resistance, R is its value. So we will be having three equations, V1 minus VA over 10, similarly VA minus 0 over 40. So that would be VA over 40, or VA over 40, or VA equal to 40. Similarly, the third equation would be V2 minus VA over 20 equal to 0. So this is how we will be getting the equations, and we will here we see that we have defined 10 minus V over 10 plus 20 minus V over 20. So these are the currents entering the node equal to current leaving the node is VA over 40. We may write it like this, or we will write it like algebraic sum by making it negative and summing all equal to 0. So this is another form of writing the equations. So here we will be getting I1, I2, I3, which are the exact same values we got in the previous KVL analysis through KVL, and if we know all the currents, we will be able to find the voltage VA. Now we have the voltage at this junction. So this is the circuit analysis. We should know the voltage and the current at every point in a circuit. So thank you very much for listening.